Okay, so this would be a review class for the last 4 video lectures. So that basically started from a discrete Fourier transform. Let me also keep this video turned off so that bandwidth issues. Okay, right. So discrete Fourier transform, the way you could look at it is, I'm sure most of you would have gone through it already. So DTFT is x of e power j omega. You take samples of it, okay? And if you are taking uniformly taking samples of it and you consider it as, let's say, x of k, then let me, yeah, here. So, so x of, if you take the DTFT of it, it would give you x of e power j omega. If you take uniform samples of it, that's what would give you x tilde of k. And suppose if you are taking the inverse DFS of it, what you would be getting, this is something we have worked out in the previous lectures also. You get a periodic sequence for which one period corresponds to x of n. So this is what we are going to exploit here. What you would be doing is one period of this x tilde of k you define as DFT. And one period of this x tilde of n you define it as x of n. That's all. That's the only difference when it compared to DFS. So if you want me to put it slightly differently, in other words, what I could tell here is you treat as if x of n is periodic by repeating it and just restrict yourself to one period of the signal. So that's another way of looking at this thing. So this is how this is defined now. X of n is equal to one period of x tilde of n, and for all the rest of the values of n beyond this length n, it is 0. Similarly, x tilde of k is periodic, but you just restrict yourself to one period of that. So all that we are doing here is we are substituting here the definitions are the for the x tilde of n and x tilde of k, the synthesis equation and analysis equation. That's all for DFT. Okay, and then we are making so DFS, if you recollect, if you want to shift, for example, that signal by a value, say m, n minus m, if you want to do it, one way is you just append, consider one period before and after, and accordingly you move it, and just then you take over one period starting from 0. If you are keeping track of everything through one period alone, we have seen even the same thing we have done with DFS also purposefully, because that would be useful here. So you need to simply take modulo operation. What we mean by that is you divide it by n, and whatever is the remainder, that's what it gets attributed to. Okay. And suppose if your value inside that for which you are taking modulo is negative value, then you take n minus that value. That's all. So then we have solved few examples here. So yeah, I want to be very brief here because we anyway have discussed it there in the videos detail. And so I think unless, yeah, as you know, the goal here is if you have any questions or doubts here, that's what we would like to discuss. So does anyone have any questions about the, so this first video was just to define what is DFT and then solve some examples. That's all. We solve those examples and then those are the definitions. So any questions here for the first video? Otherwise I'll move on to the second video. None of you has any questions? Okay, then in that case, let me move on to the second video. That was about discussing the properties of DFT. What we did there is, let's say in the conventional way we went, first is the linearity. Here you treat as if you are repeating that signal, and that's how you, it's equivalent to, in a way, when you repeat it, that should be equivalent to a periodic sequence, right? So if you have two sequences which you want to linearly combine, all you need to do is you take the same length of that. So that length could be simply max of those n1 and n2. To get that, all you need to do is simply append. If, for example, n1 is smaller, so till n2 minus 1, you append 0 here, okay? And then see, you would see there, this is when you are, when you would like to know the DFT, you also additionally has to mention how many point DFT you want to take. So that's what would tell you, essentially this is what would decide on x of e power j omega, how many samples are you taking, with which duration, or with which interval you are taking. For example, there x of k, if you take it, that's nothing but you are taking samples of it, okay, which is at an interval of 2 pi by n, and the kth sample out of that is what it corresponds to. So if your n value is more, accordingly the points which you're taking more samples of x of e power j omega, right? And we also discussed, if your n value is less than any of the lengths of these two signals, then what would happen is time domain aliasing would happen. So as long as the n value is greater than or equal to the length of the sequence, that would be fine. Okay, then we discussed circular shift, again same as what we discussed in the DFS, except that in place of n minus m there, you get n minus m modulo m. That's the only difference here compared to that. And then you already should be knowing by this time how you do this modulo operation and circular shift. Okay, say for example, this is your x of n, with n being 5, okay, and you want to shift it by 2, so that you would be writing as n minus 2 modulo 5. So how do you shift that? So this makes the shift to the right. Okay, one way you could look at is the whole signal which is at 0 would start at 2, there are 2 remaining at 3 and 4 would go to 5 and 6. So you simply could think of it as you move them to 0, and you shift the rest from 0 and 2 by a factor 2. That's how you could think of it. So initially, if this is not clear, you simply draw one period here before this, okay, whatever this 5, 4, 3, 2, and you draw it. You make a shift now, and a simple n minus 2 you do it, and just take from 0 to 4. That's elementarily in the beginning, that is fine, but later it would be good, that becomes very cumbersome, when particularly if you are doing convolution and doing it multiple times. So get used to this way of shifting as well. Okay, suppose if I had, instead of n minus 2 modulo 5, if I had let's say n plus 2 modulo 5, what would you do then? You simply take these two and you move 2 3 4 to 0 1 2, then you put it on the other side. That's all. That's what the circular shift is. Then this we had discussed in 2 3 different ways. Okay, two I mentioned now. And the same logic holds even if you are shifting in the frequency domain. Okay, suppose you are making a shift there by L. Since everything has to be in between 0 to n minus 1, what would you do? To map it back to 0 to n minus 1 by taking the modulo n operation here. That's how. So that would give you circular shift in DFT. Okay, again this is same as DFS. If you recollect DFS, there you had n times x of minus k. So in addition to that, you have here minus k modulo n. That's all. Okay, and then the last one is circular another important one you need to understand thoroughly is circular convolution. So far you have seen linear convolution, periodic convolution, and this would be the last one, the circular convolution. What it means is, suppose if you are multiplying the DFTs and then what is its equivalent on the time domain would be told, you would get it as the equivalent one you will be referring to as circular convolution. So if you recollect what it is about periodic convolution was x1 of m into multiplied with x2 of n minus m there. Okay, so here in addition to that you get n minus m modulo n. You again map it back to 0 to 5. Okay, you could actually go to periodic sequences, do their periodic convolution, and then take 0 to 5 values. That will also map here, but that will become too lengthy. So it's better you get used to performing the circular convolution right away by keeping track of just one period of the signal. Okay, that's all. Then there are some examples here. Again, suppose if shift by 2, either you could do it in this way. Again, please go through the last video if you have not yet gone through it. There I have solved a good number of examples where for examples for circular convolution also. So here I already solved a couple of examples, but you find more there also, because there you had expected to do blockwise linear convolution using circular convolution. Okay, so there also you please refer to that as well if you have not gone through it already. So then there were some examples here, and very similar to the examples, there were some problems as well here. Okay, so any questions on this one? If this is clear again, I can move on to the next one. Any questions as far as the properties of DFT are concerned? It seems there are no questions. Okay, then I will move on to the third videos. Okay, that was performing linear convolution using DFT. So purposefully, I have given some examples there in the previous video lecture where I asked you to solve some examples. There you will see that as I mentioned, in an endpoint DFT, you could vary the n value and do the circular convolution. And you would realize that when you have sufficiently large value of your n, your circular convolution would be equal to linear convolution. Why is it useful? So that's what's the motivation for performing linear convolution using DFT is discussed in the beginning of this video lecture. One important thing here is see, there is no why is it important to perform linear convolution in the first place? It's because you have you want to find out the response of any LTI system that's equivalent to performing convolution. And convolution, you could see if there are k non-zero elements in one of the things, so you have to perform k multiplications and k summations for finding out each value at each element. Suppose if one sequence is of length L1 and another is L2, if you are performing linear convolution between these two, the non-zero length of it will be L1 plus L2 minus 1. So L1 plus L2 minus 1 times so then again L multiplications are 8 plus additions you have to do. So something around assume that this L2 is just a small kernel, you could ignore it with respect to the length of the original sequence on which you want to apply. So this would be roughly of the order of L square operations you have to do. On the other hand, multiplication, if you are doing on the other, if you could do it on the frequency domain, that's equivalent to a simple multiplication, which would be of the order of L. And the efficient algorithms for computing the DFT and inverse DFT would be in order which is much less than this order of L square. So that's why most of the times you go for multiplication in the frequency domain for performing a convolution in the time domain. So that's the basic motivation for this. Then the second part is, anyway you can't do this multiplication on the DTFT because it's a continuous variable with varying omega. There is no way you could numerically do that for all values of continuous values of omega. So you would then go for doing it in for n-point DFT. Okay, you multiply them both. This is again of the order of n squared, right? Once you multiply it, you take inverse DFT, and that would in fact be equivalent to so nowhere actually you would directly do circular convolution, but this is doing equivalent of circular convolution on the frequency domain. That's what we mean there, performing linear convolution using circular convolution. It doesn't mean we would be doing circular convolution, but would rather doing circular convolution in the frequency domain. That's what that implicitly means. And then when this circular convolution is equivalent to linear convolution, then obviously this multiplication, taking inverse DFT of it and just retaining one period of this signal would give you the linear convolution result. So that's the basic idea for whole stuff here. Okay, I made some assumptions here really similar to P, but you could even, this is another way I was telling here. Suppose if you look at here, assume that this LP is a kernel, for example, a moving average kernel, which is very small. Okay, that's another assumption you could do. In that case, what you could do is, this is simply, then this is again, anyway, this is addition. So even if it is L, or this can be neglected with respect to L, anyway, it turns out to be of the order of L square. On the contrary, here, there are a couple of very basic algorithms for finding out DFT and inverse DFT. They will be of the complexity of order of L log L to the base 2. So logarithmically, at least it would reduce, a very significant reduction, computational time would be there. If you are doing n point DFT, that's equivalent to n log n to the base 2. That's why you would go for circular convolution. Okay. And then the earlier explanation was more of an intuitive thing. So we have here thoroughly worked out when would be these two would give you an equivalent result. Okay, this is what we have worked out here. This is again very simple to do it. Suppose if you are doing linear convolution, you get here this being length of L, this being length of P. The length will be L plus P minus 1 would be the length of the convolution sequence here. Okay. When will be, if this is the length, essentially you are looking at the GTFT of it, that should, at least you should take these many point DFT, is it not? Then you would be fine with it. So to achieve that, what you do is, you append, you make x1, you zero pad both x1 of n and x2 of n to this length. Okay, and take, this is your n. Now you take n point DFT, and after that you multiply both the sequences. On the result you take inverse DFT. That's all you will do. Okay, so this is also a very important discussion, is that what would happen if your n is less than this, particularly n equal to L is a very important case. This also we made analysis of it in the same thing. Okay, I guess this should be somewhere. Okay, that in one of the examples, I think the previous video lecture would discuss about that. There you would see that if you take n equal to L, and so this length being L plus P minus 1, you would see this P minus 1 points of your result. So among this n will get corrupted. So those are got corrupted. So that's what would give you. So this we particularly use, explicitly make use of this fact while we want to do blockwise linear convolution using DFT. Okay. And overlap add is the first method we would be discussing there, where we would first make the sequence to be of length L plus P minus 1 and do the stuff. And then the second approach is we make an overlap, because these many initial values would get corrupted. We divide it into blockwise such that that much of overlap is there, so that in one sequence that's the end of the sequence, in another sequence that's the beginning of the sequence. So only the DFT for the beginning of the sequence get corrupted, but you get them correctly in the first sequence. That's all. This is as far as performing circular convolution or performing linear convolution using DFT. Okay, any questions here?
Excuse me, sir.
Sorry?
Sir, I did not get how multiplication in time domain has order of n.
Okay. Multiplication in the, so see, let me put it, I'll just write it here. See, suppose I have a sequence x1 of n equal to, let's say 1, 2, 3, 4, 5. Say x2 of n equal to another sequence, or you take the same sequence, doesn't matter. Now, if I'm going to multiply x1 of n with x2 of n, okay, and suppose I need to then even do the sum also there, right? So when it has elements, n elements are there here. Okay, this also has n elements. How many multiplications I have to do? This one multiplication, second multiplication, third, 4, 5. 5 multiplications, and after that 4 additions is what I have to do. Is it not?
Sir, in the frequency domain, using circular convolution.
Yeah. So you consider this as x1 of k and x2 of k in that.
Sir, if our signal is real, then these x1 of k and x2 of k will be complex numbers.
Yeah, very good. So that's an important point. So what it will do is it will just add to 2n plus c. Suppose if I have something like 100n, plus some 10,000. Okay, these are the number of operations I need to do. Then I still would be calling it as order of n only. What I would be interested in is with varying n, how is it going to scale up? On the other hand, if I have something like n square, n square plus 1 or whatever, this I would be calling it as order of n square. So essentially, what the computational complexity tells us is, with varying value of n, is it going to the complexity, is it going to increase exponentially, or is it going to increase with the square of number of terms, or is it logarithm of number of terms? That's what the computational complexity tells us. So for example, your question is, let's say I have here a plus jb, okay, and here c plus jd. I am doing multiplication here. So that, how would I get the multiplication? AC minus BD plus J into AD plus BC. Is it not? So for each element, here I have, let's say, this is equivalent to 2 multiplications here. And here there are 2 multiplications and plus 1 addition there. Not 1 addition, 1, 2, 3 additions are there. Correct? So that means if I have n elements, so this is 2 multiplications here. So if I have n elements, for each element I have, for example, if I consider simply the multiplications, this would become 4n there. So order of 4n, I would still consider it as order of n only. Because what is of more interest, that too when increasing n is increasing very large, is the way they say it is, you are more interested in the power of n, or the exactly the term with that involves n. Yeah, my implicit assumption in the earlier expression while solving it was n x of k is real, which need not be the case at all. Does it?
Yes, sir, got it.
Good. So this, we would have done this in more detail for the FFT, but nevertheless, some of you who are interested in FFT, please take a look at Oppenheim's lectures are there on FFT. Please read, go through they are very nice. Go through decimation in time and decimation in frequency. That would be very interesting. So he does a very thorough analysis there. First, yeah, we have also done in very similar lines. You just simply take, suppose if you are multiplying 2 complex numbers, how does the complexity would be there? Addition of that, what would be required? And then once you are doing it in the Fourier, yeah, as of now, DFT, it's hard for you to realize why it would be of order of n log n. If you are doing it in the conventional way, it would be order of n square actually. So unless you use those FFT algorithms where you go through it, where you modify the implementation of those algorithms such that you make use of, for example, further the various properties of DFT, and you split it into even and odd numbers, or you split the sequence into 2 parts and then individually find out DFT. Unless you see it, you won't be able to figure out why the complexity of computing DFT and inverse DFT is order of log n to the base 2 and not n square. So those are the algorithms where you modify the way you implement those summations and additions. The computation of essentially the that definition of x of n, the way you implement, you do some mathematical processing on top of it. Does that answer the question?
Yes, sir. Thank you.
Okay, good. Any other question here for the this video lecture on linear convolution using the DFT? Okay, so if not, we'll move on to the last part. Okay, so this was performing DFT. See, so far what we have seen is using DFT for convolution is very convenient, or computationally efficient if not convenient. And next point is, how do you get the accurate? For doing that, what you should do, you should the length of each sequence should be 0 padded appropriately, such that if one sequence is of length L, another sequence is of length P, the length of each of those sequences x of n and h of n will be L plus P minus 1. Is it not? So that means you should know in advance the length of the sequence L. So imagine the case where this audio signal of my speech has been recorded. So if you want to apply DFT on it in the conventional way, you have to wait till the end, because that only will give you what's the length of the whole sequence, right? And then unless you know it and append it appropriately, you would get time domain aliasing and other effects there, correct? That's not a very efficient way of doing it, because for example, anyway, if you just look at linear convolution, let's say, oh, you have some sequence like this, and this you want to do a simple averaging filter you want to apply, you could see there, this, if this is your signal, it essentially sums up the values at a given point wherever you want to compute that value, and then the previous two values it takes in does a sum of them, isn't it? So to perform this convolution, it only depends on just its neighbors. So it doesn't really, at least when you look at it in the linear convolution, doesn't make sense for you to wait till the end. If you are doing directly linear convolution, you could have done it right away without worrying about the what is the length. Okay, but the moment we had to do it using GFT, that's where you are having this problem. So we deal this with problem into, and that's not the only reason. You might be sometimes knowing the length, but look, there for computing every value, you have to load the whole thing. You should deal with the sequence which is of length. This length could be 10,000. Okay, it's not surprising that would be of the order of few tens of thousands, because you would be taking, if you are taking, consider your 20 kilo up to 20 kilohertz you want to do it, so 40 kilohertz will be your sampling frequency, and look how many samples you have to take per second, and calculate roughly for 1 hour speech how many samples will be there. That would give you this L value. So one is indefinite length, then this x of n could be very large. What would the consequence of it? Imagine a case where this might not be a big problem if you are running on your desktop, but take a case where you are implementing it in a DSP kit, or a dedicated DSP processor, which will of course will have limitations in terms of its memory and computational capabilities. So you want to minimize things. So that's another reason why you want to do things differently. And the next thing is, if you had to, even if you could afford for having large values of sequences, even if you can afford for if you know the finite length of it, but still you have to wait to do the processing till the whole signal is acquired. Okay, sometimes probably that's not the always what you want to do. So this is where to deal with it, you divide your signal into blocks, and you manipulate these blocks such a way. So intuitively, it should already make sense to you that when it is simply depending on three things, there should be a way to exploit this, and make sure that you could get it even by dealing with small blocks. That's the very basic idea here. How you do that? For example, the whole signal, let it be going indefinitely, but imagine your length of the signal, you are going to make it into sub-signals, okay, of each of length L. So X subscript R is telling you which is this is 0th module or 0th part. This is the first signal, second, third, fourth, and so on. So what is its value with respect to the original signal is, if you want, if subscript is 0, that's the original part. With subscript 1 you want to get it, you simply add L here. With subscript 2 you add 2, and so on. So X subscript R of n would be equal to X of n plus RL. And again, the signal length being L, this is what you do for 0 to L minus 1 and 0 otherwise. Okay. Now, suppose y of n is what you wanted to compute by convolving it with h of n, the impulse response of that system. So this, now you substitute in place of x of n this value, r varying from 0 to infinity. It doesn't really matter even if you have signal on the negative side, simply this r0 would change to minus infinity, something like that. Okay, xr of n minus rl convolved with h of n. Now, suppose whatever you are getting by convolving xr of n with h of n, if you call it as yr of n, right? So this is equivalent to individually going through this length and then assume your HR of n is something like that, and you then convolve this for this L, that's equivalent to yr of n. So if you are doing the convolution for the x0 of n, that's y subscript 0 of n. You are doing for x subscript 1, this then you call it as y1. So you could see here, then this is a, then this being a linear time invariant system, you could get from that y of n by simply shifting each of them by the respective r values, a multiple of R with L, capital L, right? That's all. And then, of course, there is another thing we have to pay attention here. While you are doing this convolution, what's the length that you would be getting? Because this is what you are going to sum up, but this length is not same as the length of X or H. But here, if this length is L, this length is P, this could go to L plus P minus 1 length. Okay, so that's where you could see for varying values of R, there is an overlap of P minus 1 here. So that's all. So between any two consecutive things, there is a P minus 1 elements overlap is there, you simply add them. That's all. So that is exactly what you could do. Again, the theory we discussed it so far, you could do even if you are doing direct linear convolution, because we haven't talked anything specific here about DFT or anything. We simply have written now the linear convolution while you are splitting your signals into blocks of L and convolving each block of that L with your impulse response. So that's the expression we have written purely in the time domain itself. We haven't moved anything to the linear domain. But all we would then do, when you want to do using DFT, is you already know that this length will be L plus P minus 1. So if you make your X subscript R of n and H of n of length L plus P minus 1, then your DFT you multiply, you take inverse DFT and take one period of that, that would be exactly equivalent to what the result you get here through linear convolution. So that's all that you do here. While you would like to use DFT for performing blockwise linear convolution, you could see here there is this is the overlap which you keep adding there. So that's why you call it as block add. Okay, another method you call it as block save. Okay, so this is overlap add. That another is overlap save, which you would come back shortly. So that's all. So we have taken an example here. So this is discussed in detail again the video. First we did direct linear convolution. Second we did blockwise linear convolution. Third we did is you use your endpoint DFT here. Okay, this blocks, for example, how many blocks we have taken here? I think we wanted to divide it into blocks of 3. Okay, and this being equal to that being this again H of n being length 3 minus 1, so 6 minus 1 5. So you have to do 5-point DFT by appending the additional 2 here to x0 of n, and for H of n also additional 2, and then you do DFT. And we haven't done DFT here, but rather what we did is we were just doing a circular convolution in the time domain itself, showing that the circular convolution is same as the linear convolution. Okay, if you want in practice what you would be in fact then doing is probably for these two you take DFT, you multiply them, you take inverse DFT, that would give you the linear convolution. Okay, in examples we don't want to do all these things, so we right away now computing circular DFT to show that both of them would be same. So that's all we worked out. Then the next method is overlap save method. This is based on the fact that this is again result from the last but one video, where if your length of the sequence is n plus or p plus l minus 1, if you are using only doing a p point DFT, l minus 1 point values in the initial values would be corrected. So what you would do, you take, while you are decomposing the signal, okay, you take an overlap of here, for example, L minus 1, and anyway, in the beginning, you don't even compute the DFT at these points, circular convolution at these points, you simply take the values here. That's how you deal with how many values get corrupted. Anyway, the corruption happens in the beginning of your sequence. So you take at least an overlap of that L-1 between the blocks that you are constructing, and then you ignore the computation of those values in those sequences where it is at the beginning. That's all. So that was the example again we worked out thoroughly in the video lecture. Okay, so for example, here we considered the length of 5, and the h is anyway the same thing. So what would be, how many values would get corrupted now? Yeah, so L plus P minus, so the length you wanted to be 5, but well, P minus 1 values get corrupted, L point DFT itself you are taking, so that being 2 values would be corrupted, correct? So for that, since you have to pay attention for x0 of n while taking overlap, what you do is you also take, if your signal is something like 0, 1, 2, 3, 4, on this side you could consider as if these are zeros. That's perfectly fine. Okay, so you consider, you start with appending those many zero pad just for the first element. Okay, that's why we took these two, and then that's how you construct your sequences. And then we also have circular convolution. If you have not you're not comfortable, if it's not very clear while we discuss a circular convolution there, this solving this example should clear you any doubts there. And then we did that, we arrived at the answer, and that's of course should be the same as the previous one, and it's the same. Okay, those are the things that we discussed in the GFT, where you are doing blockwise DFT. So this is in fact how you implement DFT. So these are very practical things. Unless your capturing sequence is very small, you will not go for doing. See, convolution is essentially you have to do, as long as your system is in LTI, there is certain operation you want to do, it turns out to be a convolution. So there is no point when, particularly when you either do not know the length in the beginning of that sequence, or it's too long and you have to wait for it, you would obviously go for blockwise approaches. Okay, yeah, that's all for here. So we are done. Yeah, any questions in this from whatever we discussed? I'll just stop the recording then here. Okay.